Hi everyone, welcome to today's edition of the Learning Journal. Today I want to address one question in the last video. Okay, so when we have a quadratic equation to solve for square root of the reduced temperature, which temperature should we take? Yeah, that was the last question that we were trying to address. So to help us with that question, let's think about trying to use this Ping-Robinson equation in the first place. Yeah, how is it supposed to be used, right? How is it supposed to be used? So when we get the reduced temperature, we have a positive temperature in Kelvin. Then we divide by the critical temperature. So reduced temperature is always positive. Okay, so reduced temperature is always positive. And then when you substitute the reduced temperature back here into the square root of reduced temperature, there are two possibilities, right? For that the square root. Yeah, we can either take the positive or negative square root, and both will satisfy. When you square them both, both of them will actually satisfy this equation. Okay, when you take the square root of reduced temperature, you can have a positive or negative square root, and both will, if you square them back, you will get the reduced temperature proper. However, we usually just take the positive square root and we put it in here. Yeah, so coming back to this question of should we use the positive or negative square root. So we just did from our little thought experiment, we saw that reduced temperature or the square root of reduced temperature, we usually take the positive square root. So that's when we substitute it into the Ping-Robinson equation here. We always get the positive square root to substitute the reduced temperature to find this alpha T equation. My guess is the most likely thing is, we will get the positive square root. Okay? We will get the positive square root. So that when we actually take the roots, right? When we take the quadratic roots of this equation to find the temperature, we should get the positive square root. Okay, how do we find the positive square root here? So here's two things, right? We have we actually have a reduced temperature array here. We have a reduced temperature array, okay, that we call this function to find the real quadratic roots. Okay, so there are two roots being returned here. Okay, there are two roots being returned here, x1 and x2. Okay, x1 is basically minus b plus b squared minus 4ac square root this number. Then the second one is minus b squared minus 4ac. For real roots, okay, b squared minus 4ac must be bigger than 0. Okay, greater than or bigger than 0. So it is likely that x1 will be the number that we will want to use. Okay, x1 is the number that we want to use. Okay, so and of course we hope that this b squared minus 4ac is bigger than this negative b. Now for all for b values are for values of b that are positive, we will surely take x1, right? For values of b that are positive, minus b plus b squared minus 4ac, we can be sure that x1 is definitely the positive value. That's the first value in this array here. Okay, but now we have to ask ourselves, what is this proper value of b? Okay, what's the proper value of b? So b is right here. You can see this reduced temperature thing here. Okay, b is right here. It's psi 2 kappa square minus 2 kappa. So what is psi 2? Okay, psi 2 is this whole mess of things here. Okay, this whole mess of things here, which sort of accompanies this reduced temperature. Okay, it's very messy. Okay, but should it be positive or negative? Side 2 should usually be a positive number. You can see here v minus b over rt. Assuming b is close to 0, we can just sort of neglect the minus b here. So v over rt, that's definitely positive. And the right hand side factor here should also be a positive as well. So what's 2 kappa squared minus 2 kappa? So what is kappa in the first place? Kappa is this equation here that depends on the eccentricity factor. So yeah, it's very hard to tell. Yeah, kappa could be positive or could be negative depending upon the value of omega. Okay, so yeah, but likely omega we see from previous let's see, let's just substitute typical values of omega, eccentricity factor. Okay, so from eccentricity factor of steam, we see that omega is less than 1. Okay, omega is less than 1. And likewise over here as well. Yeah, omega tends to be less than 1. So just by inspection, kappa is usually positive. Okay, that's my gut feel. Okay, we can do it rigorously, but I'll try not to go into too much math until it's superbly necessary. Okay, so 2 kappa squared minus 2 kappa. We factor the kappa out. We factor 2 kappa out and we are left with kappa minus 1. Okay, kappa minus 1 is negative. Okay. Let me get the types. Real gases here. We call, okay. So let's put it on here. Which root do we use? Okay, which TR reduced temperature should we use? Okay, so let me just do that. Okay, we know the discriminant b squared minus 4ac should be greater or equal to 0. So okay, for real roots, so what we have left, okay, what we have is that for positive b, we will likely take this root. Okay, so we will take this root, and positive a, we will likely take this root. Okay, for positive b and positive a, we will likely take this root. Though it's hard to see, however, it is hard to see if, right? It is hard to see if A or B are positive just by one look. Okay. Okay, so let's see whether let's see whether we can simplify. Okay, we can look at B. Okay, so that's what I was doing just now. I was looking at B, and let me factor out 2 kappa for us. 2 kappa. So it's kappa minus 1. Given that kappa is usually less than 1, okay, B, we can expect, Okay, b to be more than 0. Okay, so let me rearrange this, and we'll have 1 minus kappa right here. Okay, so given that kappa is less than 1, we can expect b to be greater than 0. Okay, so that's one way of doing it. Okay, we can check the value of a, but maybe there is a simpler way. Okay, maybe there's a simpler way. Okay, so yeah, we can check the value of a so that we can see whether, you know, this is the correct root to use. Okay, or we can even better, we can actually see, we can do a little bit of yeah. Let me write the simpler way first. Okay, so the simpler way is basically if we have a positive and negative value of square root r, or square root of reduced temperature, okay, we just do a let me see. We will just do a check. We will just do a check. Yeah, we will just do a check to see whether it's positive or negative, and we'll use code to do it so that we don't have to do all this complicated math. If the computational cost isn't too high, this may be a viable approach rather than we do things a hard way. So we can sort of do, excuse me, apologies, excuse me for that. Yeah, so yeah, we can do it the simpler way. Let's see. Yeah, so let's see whether there's a simpler way. Yeah, so I'm just going to check straight whether it's greater or greater than 0, or yeah, which reduced temperature root is greater than 0. We can just check if square root t r is greater than 0. Okay, and use that root. Okay, check if square root tr is greater than 0 in the program and use the root. Okay, so maybe let's do it that way, do it the lazier way, right? So where's the reduced temperature? Okay, so here's the reduced temperature, yeah. So here's the question. You know, what's the better route to use? Okay, let reduce temperature root 1 equals to square root reduced temperature array. We'll get the first one, and we'll also get the second root. Okay, and then I'm going to just do bacon test. Okay, so that's like cargo watch, but bacon is a lot easier to work with. Okay, so these two are roots we can test, right? So let reduced temperature correct root, this will be a ratio. Okay, this will be a ratio. Now we can do a simple if statement. If reduced temperature root 1, we can do a, yeah, this is the sign of the number. Well, let's see. It's sign positive. Yeah, we have a is sign positive method. Okay, so if the sign is positive, this is the method we can use. So if the sign is positive, it means it's greater than 0, or greater or equal to 0. I mean, this is one way of doing things. Okay. So if the sign is positive, we should be able to get it. Yeah, we should be able to assign this value to the correct root. Reduce temperature correct root equals to reduce temperature root 1. Okay, so that's checking. So the first part here is to check if the first root of the reduced temperature is positive. If so, we use that root. Okay, else if reduced temperature root 2 is signed positive. If this one is positive, then we will assign the second root to it. Okay, so that's all we are doing here. Okay, we just let the code check the temperature for us, and then we will not do anything here. Okay, so here's the else clause. If neither of the roots are positive or negative, then we'll need to return an error. Return error. Okay, we'll need to return our let's see, Ping Robinson guess error. Okay, then you can do a no real temperature root error for that. Okay, so if we have no if neither of these roots are, or neither of square root t is greater than 0, then I think the no real temperature root should I mean, this is kind of the error, it's the closest error. No, of course we have two real roots. If both roots are like negative, both square root t's are negative, I think that there's something wrong with the equation there. So okay, maybe we'll not do no real temperature root. We'll call this both reduced temperature roots are negative. Okay, both reduced temperature root negative. So this is an error I want to return. Okay, so let's go back to our Ping Robinson equation of state. Oh, we're already here. And then we will just we'll just do this. We'll put the thing here. Cubic EOS error. And I'll put both reduced temperatures are negative. And then we can we put the correct root down here. Okay, and then we should be able to find the correct gas temperature. Let's see what the test is showing us. Okay, so it's showing us 889 is the so-called correct root. Okay, I don't know whether this works, but it looks good enough. It is close, but it's not close, you know, close. Yeah, but it's somewhere, it's not as far off as maybe 200 degrees. Maybe it's a good thing. Okay. So let's see getting the steam temperature. Let's reduce the error to maybe 1%. Accurate to within 1%. Okay, doesn't work. Let's try 2%. Okay, 2% it seems to be okay. Okay, so if 2% is good enough, then okay, we might be able to use this Ping Robinson equation of state. And I guess Ping Robinson equation of state deviation from a steam table is roughly around that range. But I need to go and check some literature for that. No, but anyway, you can go and look in literature to see if this error bar is too large. But I think for now, for the sake of this video, I think that's good enough. It does show what I want to calculate, and the values are not terribly far off, like what, 5% or 10% off. Okay, maybe it's like 10 degrees C off, 10 Kelvin off, but maybe that's okay. Okay, depends on your application. So for now, I'll just stop here because I think most of the things done. If you do find problems with this way of doing things, I mean, leave a comment or something like that. Okay, but for now, I'm not gonna do anymore. So okay, for reduced temperature square root, we use the positive square root root. We use the positive square root value. Okay, so that's what we are doing here. Okay, I'll delete this, and I think I'll call it a day for this video. Okay, thanks.